All right, so great pleasure to have Grant Remmen all the way from Berkeley today. He's going to talk to us about weak gravity, entropy, and Dyonic black holes.
Well, thanks very much for having me. It's a pleasure to be here visiting Davis. So today I'm going to talk to you about the connections between weak gravity conjecture and black hole entropy, both in the context of electric and magnetic black holes, and indeed for black holes that are both electric and magnetic. This talk is going to be based on two papers that I wrote in collaboration with Cliff Chung and Junyu Liu of Caltech, one from last year and the other one that is soon to come out, either this month or just possibly next month. So first, by way of introduction, let me set this up by talking to you about the Swampland Program. So in theory space, in the space of low-energy effective field theories, we have some landscape of theories that string theory hands us. And we have a swampland, a set of quantum field theories that naively seem all right. You can write down their action, but for one reason or another, string theory never generates these actions as a low-energy limit. So an interesting question is, what is the boundary between the landscape and the swampland? How do we define the set of quantum field theories that are healthy, that are consistent with ultraviolet completion with gravity? So there are two approaches to finding the boundary of the landscape. The main approach is to do kind of a top-down argument by looking to data, in this case data being UV-complete examples from string theory, and making conjectures. And the most celebrated example of this is the so-called weak gravity conjecture proposed by Nima Hamed and others in 2006. But a parallel question you can ask is a bottom-up question, which is, what bounds a set of consistent EFTs in the first place, independent of string theory? So just what quantum field theories are infrared consistent in and of themselves. And it turns out that there are actions you can write down that are secretly infrared sick. And there's been a whole program of bounding actions in this way using principles like unitarity, causality, analyticity of scattering amplitudes, and the like. And in this way, people, including myself, have bounded terms in higher curvature gravity, massive gravity, and even simple terms like d5 to the fourth and f to the fourth couplings. But a really interesting question is whether these boundaries are ever the same. That is, can we ever run up against the boundary of the landscape purely from the infrared? That is, does the landscape ever abut the end of the space of consistent low-energy EFTs themselves? And in this talk, I'll argue that that is indeed the case in the context of the weak gravity conjecture. But I'm not going to use any of these other principles like unitarity, causality, or analyticity. Instead, I'll use a new infrared consistency argument related to black hole entropy. So, okay, what do I mean by the weak gravity conjecture? There are several versions of the weak gravity conjecture floating around out there in the literature. So to be concrete, for the purposes of this talk, I'm going to be talking about the weak form of the weak gravity conjecture. And for now, you can just think about the weak form electric of the weak gravity conjecture, which is that for any abelian gauge theory coupled consistently with quantum gravity, there has to be a particle or some state, not necessarily a particle, but just some charged state of charge q and mass m, such that q over m is bigger than 1. And so for such a state, gravity is the weakest force, because two of those states will repel each other rather than attract. The original justification of the weak gravity conjecture, aside from string theory examples, was from black hole decay. You can convince yourself easily using charge and energy conservation that a black hole can only decay to products with yet higher charge to mass ratio. So if you want an extremal black hole to be able to decay, you need the weak gravity conjecture to be true. There has to be some lighter state with charge to mass ratio bigger than 1. Now, why should black holes decay? Well, the answer lies in pathologies with black hole remnants that we won't have time to get into, but this is, you should just keep in the back of your mind as sort of the moral justification for why people wanted the weak gravity conjecture to be true in the first place. But we're going to argue for it using a completely different reason. Okay, so now let's think about thermodynamics. I want to do a thermodynamics thought experiment that will give you intuition for the argument that I'll make later. So consider two systems in the same macro state, but with different microstates. So two systems, same energy, for example, same macroscopic composition, but where the entropy is different because one of the systems, the system on the right, has extra microstates. So some extra internal small distance degree of freedom that we've integrated out, but that contributes to the entropy. So you would expect the system with extra microstates to have greater entropy. So delta S is positive. We can think of this same thought experiment in the context of black holes. On the left, we have a theory without higher derivative terms, so just pure Einstein-Maxwell theory. On the right, we have Einstein-Maxwell corrected by higher curvature terms. It's an effective action, and we generate these higher curvature terms by integrating out some massive states in the quantum field theory. And so you might expect then that the black hole on the right should have a larger entropy than the black hole on the left. And we'll indeed see the Euclidean path integral argument that that's what happens. But why should the entropies... Pardon?
What are you holding?
I'm holding the charge and mass fixed as measured at infinity. So you can measure the charge and mass just by fluxes at infinity. So the higher curvature terms don't correct the definition of charge and mass because you're just fixing those using the ADM formalism. But there are two reasons why the entropy changes in the theory on the right. One is just by Wald's formula. There are extra explicit terms in the entropy because you differentiate the action with respect to the curvature tensor. But the other reason is that just the area of the black hole on the right is different than on the left, because by adding these higher curvature terms, we've changed Einstein's and Maxwell's equations, and so when we hold the charge and mass fixed, we change the radius at which the horizon appears, and so the area changes. So we have to take into account both of those effects to compute the entropy.
How are you going to do?
Pardon?
Perturbatively in higher derivative?
Yeah, perturbatively in higher derivatives. So we care about this to first order in the Wilson coefficients of the higher derivatives. Right. So what theory do we want to work with? Well, let's work with the first non-trivial terms that appear in the effective field theory of a photon and graviton. So we integrate out all the massive states, and we're left with a photon and graviton interacting via, at leading order, terms that are fourth order in derivatives. So you have f to the fourth type terms, of which there are 2, you have rf squared type terms, of which there are 3, and you have curvature squared terms, of which there are also 3. And these coefficients are a priori unknown. Any other type terms you can either rearrange to be total derivatives or terms that involve currents, which we can drop because we'll be considering backgrounds that don't have explicit currents, or terms that are already here. All right. So what we want to do is we want to prove positivity bounds on various combinations of the Wilson coefficient Ci. Now that doesn't sound like it's very related to the weak gravity conjecture right now, but it'll turn out to be related to weak gravity later. But for now, let's just try and bound these higher dimension operator coefficients. All right. So first, I want to convince you why the entropy shift should be positive when I add these higher derivative terms to the theory. So any proof involves assumptions. So for the purposes of this proof, let me state my assumptions really clearly. Assumption number 1 is that there is some quantum fields phi. Phi is not necessarily a scalar. I'll just write it as phi for convenience. So some quantum fields at some mass scale m phi, satisfying m phi much less than lambda, where lambda is the scale at which QFT breaks down. So lambda is the string scale, if you like. In general, much smaller than the Planck scale if we're weakly coupled. All right, and the Planck scale is the scale where gravity gets strongly coupled, at which you have black holes appearing. So the states we're integrating out are not stringy states. They're states that live well within QFT. So just like you would normally do when you integrate out some massive state to obtain an EFT, as you learn in your quantum field theory class. We'll further assume that the fields phi couple to photons and gravitons in such a way that the higher dimension operators are generated classically, i.e. at tree level. So operators like phi r and phi f squared. So we integrate out phi and we generate r squared, rf squared, and f to the fourth terms. Now again, I'm just writing this schematically. Phi might have Lorentz indices floating around, so it might be some massive spin 2, phi mu nu coupled to r mu nu, for example. But nonetheless, we'll assume it couples at tree level. So that means that the CIs will go like 1 over m phi squared. So they're a QFT effect, and they're much, much larger than the 1 over lambda squared quantum gravity slop terms that we generically expect to be present even in the pure Einstein-Maxwell theory. So when I talk about the pure Einstein-Maxwell theory, I don't mean that there are no higher derivative terms in that theory, because they're going to be generated by quantum gravity anyway. But the quantum gravity terms are just much, much smaller than the terms that are being generated in QFT here. Couplings like this are very generic in the landscape of string theory. For example, if you break supersymmetry, you tend to generate masses of the dilaton at scales of order the SUSY breaking scale, so you tend to get phi r terms fairly easily in string theory. So this is not a strong assumption. Finally, I'm going to...
Your CI coefficient of
the higher dimension operators.
And you want them to be at some scale 1 over lambda, is not constant?
So the CIs are going to scale like 1 over the mass squared of the stuff that I'm integrating out. So they'll be much, much bigger than 1 over m Planck squared suppressed stuff. The r squared terms won't be Planck suppressed. They're suppressed by whatever we're integrating out.
Aren't you contradicting the argument of command methods and the other one on the same?
Let me see.
You
No.
argue that the causality argument precludes these kind of terms in the effective field.
So causality precludes certain terms in the EFT, but not all terms at order at fourth order and derivatives. For example, in the standard model, we have an f to the fourth term that you generate by integrating out the electron. Now, that's integrating it out at one loop level, but nonetheless, you can generate, even in our own universe, f to the fourth that is suppressed not by the Planck scale, but by a much, much weaker scale.
Let's take your theory and do field redefinition, right, or Gauss-Bonnet stuff.
Right. So you have where you have trouble is in generating the Weyl squared term from.
I have a trouble generating Gauss-Bonnet.
Right. Gauss-Bonnet is Weyl squared up to field redefinition invariance. Yeah.
That's the only fourth order derivative term there is after field redefinition.
No. You can generate just pure Ricci scalar squared.
You remove the field redefinition.
But when you field redefine, where does it go? It doesn't go into any of the other r squared terms, but it goes into f to the fourth. Only if you have a vacuum theory. If your theory is not just vacuum, if your theory contains Maxwell fields, field redefining r squared doesn't remove it entirely, it shoves it into f to the fourth. So you can't get rid of f to the fourth that way.
Fine.
So
But this is an answer to my question. How is your argument consistent with
all I need for this to work is for there to be some contribution to some of the CIs that is suppressed by a scale that is lower than the Planck scale, which is a very mild assumption. Like I said, if you have a dilaton in your theory, it'll couple to phi r. Make the dilaton massive, integrate it out. Now you have an r squared term that goes like 1 over the dilaton mass squared. Field redefine if you like, and now you have an f to the fourth term that goes like 1 over the dilaton mass squared. That's all I need for the argument to work. Okay. Finally, I'll be considering black holes that have charged mass ratios bigger than root 3 over 2 for reasons that will become clear later. Okay. So now I want to compute the entropy for the black hole using the Euclidean path integral. So I can write the free energy in terms of some path integral over the UV action I. So I tilde is going to be the Euclidean action of pure Einstein-Maxwell theory. Delta I is the shift in Euclidean action. And I can just write the EFT Euclidean action in terms of some UV action where I do the path integral over the phi fields. Now, on shell for the black hole in the perturbed theory, phi isn't 0 on shell. Instead, it's of order r or f squared by the equations of motion, since it couples at tree level. But just as a math question, we can ask what happens if I go off shell in a particular direction. And the direction I'm interested in is setting phi to 0. So if I take some on-shell configuration and then set phi to 0, I go off shell, I can just evaluate the Euclidean action there and see what I get. And just as a math statement, if I set phi to 0 in the Euclidean action, I get back the Euclidean action evaluated at that same metric and gauge field configuration for the pure Einstein-Maxwell theory, because I've just turned off all those phi r terms in the Euclidean action. So this is a simple observation, but it's important in that it will allow us to compare the Euclidean actions and ultimately the entropies for two different theories while actually secretly working just within one theory. Right, so here's how we want to construct our free energy inequality. So by the saddle point approximation, minus log z of beta is just the UV Euclidean action evaluated on the classical solutions with periodicity beta. If the saddle point is a local minimum, which I'll come back to that, but if the saddle point is a local minimum, this is less than setting phi to 0 and some other solution for the metric and gauge field, again with periodicity beta, which by the relation I just pointed out is just equal to the Einstein-Maxwell Euclidean action evaluated at that same field configuration, which by the saddle point approximation again is just the free energy of the background theory for a black hole with charge and mass corresponding to inverse temperature beta. Now that's not the free energy of a black hole with the same charge and mass as in the original theory, because the temperature shifts when we add these higher curvature terms to the equation of motion. But we can take into account the temperature shift to write log z tilde of beta in terms of log z tilde of beta tilde. And we use some thermodynamic inequalities to write that in terms of mdm of delta S. And we put everything together, and ultimately our free energy inequality turns, after running through some thermodynamic identities, into simply the statement that delta S is positive, which is what we wanted to show. So the only extra thing I've added here is that I needed the saddle point to be a local minimum in field space, which means that I have to be considering a black hole that's thermodynamically stable. Now, Schwarzschild black holes are not thermodynamically stable. Aside from the conformal mode, which is just a gauge artifact, there are real bona fide instabilities in the Schwarzschild black hole. But the heat capacity turns positive if I take Q over M bigger than root3/2. So that means there aren't instabilities, it's been shown, in black holes where Q over M is bigger than root3/2. And so we get this, this local minimum requirement that we needed. So we're considering sufficiently highly charged black holes such that the argument works. So we can see how this works in a particular example. So take higher dimension operators completed by a massive scalar field phi. So we can write down the Euclidean action, write down the equation of motion for phi, and generate the low energy effective field theory. And we see that the thing that we wanted to be negative is indeed strictly negative. It ends up being a perfect square. So we have the relation among Euclidean actions that we wanted. Another comment before I move on. So in the explicit example we looked at, the signs of the couplings depended on the absence of ghosts or tachyons in the UV completion. That's what allowed that term to be negative definite. And so that means that delta S being positive is really connected with the usual unitarity arguments, which also hinge on the absence of ghosts or tachyons. So it would be interesting to see if there are connections between the bounds we'll derive and other IR consistency bounds on couplings that are derived from the more usual methods of unitarity and analyticity. Not only that, you can apply our monotonicity argument step by step. If you're generating r squared or f to the fourth terms using states that are widely separated in mass, if you have some big hierarchy and you're passing through mass shell after mass shell independently, you can add up all the delta S's and you get some what apparently looks like RG flow from the UV to the IR. And indeed, this would be a bona fide C function if our argument holds at loop level, which I haven't proven, but that we suspect is true. Right, so...
Is the statement actually explicitly true in examples?
Pardon?
Is the statement actually explicitly true in examples?
In all the example tree-level completions we've looked at, the statement is true. Which I'll actually go through a bunch of examples near the end. But yeah, we do a lot of consistency checks.
Not if you do the Euclidean analysis, but use the Wald prescription.
Yeah. Like just we can actually just look at example UV completions where I take, say, either a scalar or a pseudoscalar or a massive spin 2 or what have you, and integrate it out and just see what are the Wilson coefficients and do they obey our bound, and they do.
No, I just meant the delta F being positive.
Yeah. They
Some will end up using the Wald prescription for two black holes, including
Yes, but you need to know what are the Wilson coefficients. The delta S is not positive for arbitrary Wilson coefficients.
I understand.
But for all the examples that we know of, it is positive. All right, so now let's actually compute delta S. For convenience, I want to rescale the couplings. The CIs I'll rescale using various powers of the Planck mass to write them as DIs. I do this because now all of the DIs have the same mass dimension. They all go like 1 over m phi squared. Now, what I want is to turn delta S being positive into a bound on the Wilson coefficients, into a bound on the CIs. In order to do that, I have to guarantee that the linear order correction coming from the CIs is indeed the dominant contribution to delta S. And there are other contributions that you might worry about in delta S. For example, renormalization of Newton's constant, which goes like m phi to the d minus 2, or loop level completions of the gravitational higher dimension operators, which you can figure out how those scale with m phi and the Planck mass. Indeed, gauge interactions will contribute similarly. So for example, integrating out the electron, which you integrate out at one loop to generate f to the fourth, the scaling goes similarly, but it's enhanced by a power of the charged mass ratio of the electron, in this case q over m to the fourth. So it's even bigger if the particles already satisfy the weak gravity conjecture. But that isn't interesting, so we'll assume that the particles either fail or marginally satisfy the weak gravity conjecture, because otherwise we'd be done. So, okay, we can write out for a black hole of size rho and of charge roughly equal to its mass various corrections to the entropy. We have the Bekenstein-Hawking entropy, we have the loop correction to G Newton, we have the loop correction to delta L, and we have the tree contribution to delta L. So this is the thing we care about. It's automatically going to be bigger than this, but we want it to be bigger than this so that we can use delta S being positive to place bounds on the higher dimension operator coefficients. Well, the term we care about dominates, provided that the black hole isn't too large. It has to be large enough to be within the regime of the EFT so that our derivative expansion doesn't break down. So rho has to be much bigger than 1 over m phi. But it has to be much smaller than 1 over kappa m phi to the d over 2. So what saves us here is the fact that we have a two-scale theory. There's the Planck mass and m phi, and so there's a window in which we can take the black hole and where we win, provided that m phi is much less than m Planck, which is what we've been assuming all along. Okay, so having said all that, we can now happily compute delta S. As I said before, we're defining the charge and mass at spatial infinity, so that means any corrections from the higher dimension operators doesn't affect the definition of the charge and mass. I'll go to relativist units where there are weird factors of root 2, just so that q over m equals 1 corresponds to an extremal black hole. Let me also define a parameter psi, which is root 1 minus q squared over m squared. Everything is just nicer in terms of psi. All right, so we're taking the Reissner-Nordstrom black hole as our background. So the unperturbed solution has a metric that should be familiar. And the extremality condition, the usual extremality condition is that q over m is less than 1 to avoid having a naked singularity. So what we want to do is compute the metric of the perturbed black hole under the corrections to the Einstein and Maxwell equation. So luckily, how to do this has been worked out, because for spherically symmetric metrics, the Ricci tensor is invertible. So we can use that to rewrite the TT and RR components in terms of various integrals over the Ricci tensor. And we can treat the perturbed Einstein equation as just the usual Einstein equation, but with a funny source term. So all of the contributions from delta L, all of the higher dimension operator contributions, just live in changes to the source, T mu nu. So T mu nu has two components. There's a gravitational component just from the correction to the Einstein equation. And there's a gauge field component coming from inputting the perturbed gauge field into the background energy momentum tensor. So the perturbed gauge field comes from the nonlinear corrections to Maxwell's equations. So we can just compute that. We get the metric part of the energy momentum, and then the perturbed Maxwell equations, and we put all that together and compute the metric to leading order in the Wilson coefficients, and we get the following. So here's the RR component. The TT component looks similar, but slightly different. And we can read off where the horizon is by just finding the zeros of this to leading order in the DIs. All right, so having done that, we can compute the Wald entropy. So the Wald entropy will have three components. There's the usual Bekenstein-Hawking component, just A over 4G. Then there's the interaction contribution, which are the explicit corrections coming from the Wald terms. And finally, there's the shift in A over 4G. So we want to compute each of those. All right, we do that, and delta S interaction just scales with the background entropy, 1 over the mass of the black hole squared times some function of the DI and psi, the charge to mass ratio. The shift in the horizon we can compute similarly. But one thing that you should note about the shift in the horizon is that it scales like 1 over psi. So that means in the extremal limit, when psi goes to 0 and q over m goes to 1, this shift in the horizon blows up. That means that taking the exact extremal limit causes a loss of perturbative control. So we have to ask, how close to extremal are we allowed to push this? Well, we can check. We can demand that the shift in entropy be much less than the background entropy. And we find that all this requires is that psi is much, much less than m phi squared over m Planck squared, which can be really, really small since m phi is much less than m Planck, so we're still allowed to take the near-extremal limit. Indeed, if we impose a stronger requirement, which is that the shift in temperature be much, much smaller than the background temperature, this just requires that psi be much bigger than m phi over m Planck, so it can still be taken to be small. So that means we can still take the near-extremal limit without losing perturbative control. All right, so let's put all this together and generate new positivity bounds. So the total black hole entropy shift is some function of the di's and psi. And imposing our entropy bound, that delta S is positive, gives us, rewritten in terms of this funny-looking combination of coefficients, gives us a bound that lives in the space of d0, d3, and d6. So we have an infinite family of new consistency bounds on the Wilson coefficients of the EFT. This has to be satisfied for all psi between 0 and 1/2. That corresponds to black holes that have positive heat capacities. So we can take a look at what the excluded regions look like, depending on whether D3 is positive or negative, and it looks like this. Now, that's interesting on its own, just to bound EFT coefficients, but I promised you a connection with the weak gravity conjecture, so let's see where that comes from. So in the near-extremal limit, the bound simply reduces to D0 is positive, D0, that particular combination of the DI's that showed up. But this is connected to the weak gravity conjecture in the following way. When you perturb the Einstein-Maxwell theory, when you change Einstein's and Maxwell's equations by adding these higher derivative terms, you change the space of allowed black holes. You change the set of black holes that have no naked singularities. Instead of Q over M being between 0 and 1, Q over M is now allowed to be between 0 and 1 plus or minus epsilon, where epsilon is something that goes like the DI's and that we can compute. So we compute it by imposing the horizon condition. So the horizon, the metric component of the near-extremal black hole should vanish. And we can write it in terms of the background black hole, the shift in the metric, the shift in the horizon, and the shift in charge to mass ratio. And putting this all together for a near-extremal black hole, we get that the shift in extremality bound should look like minus delta G over the z derivative of the background metric component. And just by direct computation, it turns out that delta Z goes like that same exact combination of Wilson coefficients. It goes like D0, which is amazing, because that means that since the same combination shows up, delta Z is positive, so that means there are black holes in the theory with Q over M ever so slightly larger than 1. So the black holes on their own satisfy the weak gravity conjecture. So the big extremal black holes are able to decay to smaller, lighter extremal black holes that have slightly higher charge to mass ratio, and so on all the way down. So the whole tower of exactly stable states collapses.
Sorry, but did you say you were looking at Q over M bigger than root Q over 2?
Pardon?
Did you say you were looking at Q over M bigger than root Q over 2?
For all the black holes for which I derive bounds, Q over M is between 1 and root 3 over 2 at the, between root 3 over 2 and 1 at the classical level. This is now the correction to 1. So now I'm looking at starting with a black hole with Q over M equals 1 and seeing what is its correction under the higher dimension operators. So if I plot Q over M versus M for the states in the theory, in the uncorrected theory, the allowed states are between 0 and 1 here. But in the corrected theory, it would have been between 0 and one of these two lines. It had to look like one of these two lines, but we know by self-consistency of black hole entropy that actually you get the upper line, not the lower line. So that means these black holes get to decay to these, and so on, all the way down to something that happens near the Planck scale where everything breaks down and we can't say anything more. Right. So that appears somewhat magical. Why did the same combination of D0, why did the same combination of coefficients appear? Well, the reason is from the horizon condition. So for a near-extremal black hole with Q and M fixed, delta Z is 0, so delta rho, the shift in horizon, went like minus delta G over the R derivative of G. for the exactly extremal black hole, delta z went like minus delta g over dz of g. And since the radial component of the metric is space-like, the r derivative of g is positive. And since the metric dictates a gravitational potential, which decreases with m, dz of g is positive, so delta rho and delta z have the same sign. And finally, for the near-extremal black hole, since the change in entropy is just dominated by the shift in area, delta S scales with delta rho, which scales with delta z, and so they're all positive simultaneously in the near-extremal limit. So the same combination of coefficients was forced to appear. So we can actually generalize this to theories that contain multiple abelian gauge fields. So picture a state charged under multiple abelian gauge fields as being represented by a vector in charge to mass ratio of space. This is some vector z. That means the set of all large black hole states is the unit ball, the set of extremal black holes is the unit sphere. And the generalized weak gravity conjecture you can show is that the unit ball should be contained in the convex hull of lighter states. So now, for us, lighter states are just lighter black holes. So if we run through the argument for the multiple abelian gauge theory, since the metric only depends on the magnitude of this vector z, our earlier argument goes through as before. And now we just write delta z as the delta z vector dotted into the unit vector. And that means that delta rho is positive if and only if dz dot z tilde is positive. So for a finite mass charged black hole, the unit ball of black hole states, it just expands in all directions under the action of these higher dimension operator coefficients. It doesn't expand by the same amount. The couplings can be different, but it's forced to expand in every direction in charge space. So that means even the generalized weak gravity conjecture is a consequence of self-consistency of black hole entropy. I can just tell you quickly that all of this generalizes nicely to arbitrary dimension. If we can write down the metric, everything will be much nicer in terms of a variable x, which is r to the d minus 3. For thermodynamic stability, we'll now need psi less than d minus 3 over d minus 2. We can compute the shift in metric as before. Everything gets dressed with ugly functions of the dimension. Similarly, we still have perturbative control, provided that psi is much bigger than some power of m phi over m Planck. So we can still take psi near 0, so we can still take the near-extremal limit. Similarly, we can check the shift in the temperature. And finally, we get the total black hole entropy shift, which we can rewrite using some funny linear combination of the di's that we define as our new d naught. We can rewrite as something simple in d naught, d3, d6 space. So we still have a bound on those three coefficients, and they're required to satisfy this bound for all psi between 0 and d minus 3 over d minus 2. And as before, we can take the near-extremal limit, and we again get that d naught is positive, and the shift in the extremality condition of the black hole again scales like d naught. So we again find the weak gravity conjecture in arbitrary dimension bigger than or equal to 4. So now I want to talk a little bit about Dyonic black holes. So in d equals 4, there's another possible generalization direction we can do. We can think about compact objects that have not only electric charge but also magnetic charge. And the solution for the metric is the same. You just send q squared to q electric squared plus q magnetic squared. So that's simple so far. And for convenience, let me define q electric as q cosine alpha, q magnetic as q sine alpha. So I'll define alpha as some Dion angle. And I'm taking polar coordinates in this space. And I can just compute what the perturbed solution is. So this ends up being non-trivial because even though the pure Ricey-Nordstrom solution is simply related for electric, magnetic, or Dyonic black holes, the perturbed solution can be quite different. So I have to solve the perturbed Maxwell and Einstein equations simultaneously. But we can do that, and we get the TT and R components of the metric. We can put that all together, running through the Wald entropy calculation as before, to compute delta S in terms of the DIs and psi, accounting for both the new explicit Wald interaction terms and the shift in the horizon radius. And putting it all together, we get a new consistency bound. So our old bound is subsumed into this new bound. It's a bigger space of bounds. There's two parameters, both the angle and the charge to mass ratio psi. So I'll define this function b of psi alpha, and I get some bound that lives in now a space of 4 different parameters. There's d0, d3, d6, and a new parameter d9. Where I'll define d9 as this new combination of higher dimension operator coefficients. So it's a 4-dimensional bound. And for alpha equals 0, this indeed reduces to the electric bound we found before. So the excluded region in the space of d3 over d0, d6 over d0, d9 over d0 looks like everything outside of this wedge. So this cone coming out of the board is what's allowed. So that's the set of bounds plus the fact that d0 is positive. Another way of looking at it is that you can show that d6 is bounded from above by various linear combinations of d0 and d9. So d3, the coefficient of Gauss-Bonnet, just drops out in this limit. And what we know is that d6 can't be much, much larger than d0 and d9. It can only live in one of these two lobes. Here, red corresponds to bounds coming from electric black holes, purple corresponds to bounds coming from magnetic black holes, and green are the equally Dyonic black holes. All right, so let's see how this ends up being related to the weak gravity conjecture. Because the weak gravity conjecture can be generalized to not just be a statement about electrically charged objects, but it can be a statement about magnetically charged objects, that magnetically charged objects should repel, or there should exist some magnetically charged state that repels. And indeed, we find that that's true. If I compute the shift in the extremality condition for Dyonic black holes coming from the higher dimension operator coefficients, I again get some combination of coefficients that equals my bound function in the extremal limit when I send psi to 0. So that means delta z is indeed positive, and consistency of black hole entropy even proves the Dyonic version of the weak gravity conjecture. So now let's think about some examples in consistency checks. And this goes back to your question of, in explicit examples, let me compute delta S and let me verify that it's positive. Or equivalently, let me compute the Wilson coefficients for various theories and verify that they live in our bound space. First though, let me do another consistency check. So let me consider a general field redefinition of the metric. So I'll shift g mu nu to g mu nu plus some number times r mu nu plus some other number times g mu nu r plus f squared mu nu. So there's 4 different shifts I can do. And this has the effect of shifting the action, which means that it has the net effect of scrambling the higher dimension operator coefficients among each other. So if someone comes up to you on the street and says, here are my Wilson coefficients for my Einstein-Maxwell effective field theory, that's not, in general, physically meaningful. They're only physically meaningful modulo all of these different possible shifts. What that means is that there are exactly 4 combinations of higher dimension operator coefficients that are invariant under this transformation, and they're exactly the d0, d3, d6, d9 that we found before. So our bound can be written purely in terms of things that are invariant under field redefinitions. And this provides additional evidence for our bound. Not everything is invariant under field redefinition. The metric is obviously not invariant under field redefinition. Areas are not invariant, but amplitudes are invariant. And it turns out our bound is also invariant. So it's like an amplitude in that sense. Furthermore, our bound respects electromagnetic duality in a nice way. So if I swap f and f tilde, that has the net effect of changing the Wilson coefficients. It changes d4, d5, d6 into these new coefficients. That is, it changes d0, d3, d6, d9. And so I should see that in the bound. So if I replace di with di tilde in the bound, that should be equivalent to swapping electric and magnetic charges, or equivalently to swapping the Dion angle alpha for pi over 2 minus alpha, and that's indeed what we find. So that's a verification that we're solving the perturbed Einstein and Maxwell equations correctly. So, okay, now let's look at example completions. So for a scalar completion, so I have some massive scalar phi. It can couple to r or it can couple to f squared. And right now let me have it coupled to both with arbitrary couplings. I can integrate it out, and I can get the higher dimension operator coefficients di I can write them down in our preferred basis, and what it generates is only D0. It does not generate D3, D6, or D9. So let me check in terms of our bound what that looks like. So b of psi alpha, that function that's supposed to be positive, is indeed manifestly positive. It goes like b squared times cosine squared to alpha. So for the scalar completion, it works. Well, what about a pseudo-scalar completion? So let me have some parity odd scalar coupling to FF dual and coupling to the equivalent for the curvature tensor with, again, arbitrary coefficients, A phi and B phi. And I can compute the Wilson coefficients again, and this guy generates not D0, it generates only D9. And indeed, again, our Dyonic bound ends up being manifestly positive. It ends up scaling with B squared.
You want to argue that A phi and A phi fields are neutral because they can usually find a way? Coefficient of phi r.
That's not quite why they don't show up. They don't show up because both r tilde and r in the previous example are exactly 0 for the background that we're looking at.
But you might start worrying if you can change. These guys can have arbitrary sign and they're unconstrained, and there are solutions where the entropy of let's say neutral black holes, neutral black holes would actually be smaller than the entropy of
We can't say anything about the entropy shift of neutral black holes. Because neutral black holes are...
But you tried using a general argument at the beginning, which is what I was skeptical about.
Pardon?
You tried using a very general argument.
But that very general argument did not apply to neutral black holes.
No, you started by saying that we integrate our massive fields and entropy should increase.
That was the heuristic argument. The real argument is the Euclidean path integral argument that I went through.
That would have been true for neutral black holes.
No, because that argument needed that the saddle point was a local minimum, which is not true for neutral black holes.
Let's run this argument maybe after this.
Okay, sure. So then what are you saying?
Then can't I decrease the entropy by changing the sign of K phi?
Well, not in this case, because the entropy only scales with B phi. It's independent of A phi in this case.
No, I'll just find two solutions in the theory with Einstein-Maxwell if A and the Pearson brings a scalar coupling. Different solutions with the same energy. One with the theory with A phi 0 and the other with the theory with A phi negative.
Are you talking with adding a cosmological constant?
Yes, I am.
We don't know how to do this argument yet with a cosmological constant.
I mean, you have path integral argument. You just give
No, it's not that simple, because adding a cosmological constant changes the asymptotics, which is and the asymptotics are what's defining your canonical ensemble in this case.
I have a well-defined canonical ensemble in ADS, right? I mean, anyway, you're doing a microcanonical count, but you're counting entropy, you're fixing energy and charges.
Right.
You're saying what solution dominates for fixed energy and charges.
Right.
I'm just giving you a counterexample, which I haven't checked this, but it seems reasonable to expect that for one sign of K phi, you can decrease the entropy while giving an argument.
I don't claim to have an argument yet for ADS, because the thermodynamic identities that I wrote down all change in ADS, because there will now be a pressure. Everything will change once you add a CC. It is not trivial to add a CC to this.
The CC can't enter thermodynamic, the CC is just fixed.
Right, the CC is fixed, but with a CC, the bound will change. Can you give me a counterexample with 0 CC? So playing within the same regime we're talking about.
Not all the top of my head.
Yeah. Okay. So here's another example. Spin 2 completion. A massive spin 2 can couple in 4 different ways. You can couple to r mu nu. It can couple to r g mu nu. It can couple to f squared mu nu, or it can couple to g mu nu times the trace of f squared. But those last two couplings can't be arbitrary. They have to come in the form of t mu nu. You can prove this using scattering amplitudes. So if you want the UV completion to be a bona fide UV completion, that means it has to reduce the hard behavior of the amplitude at large momenta. The scaling of the amplitude with momentum at large momenta in the UV completion should not be worse than the scaling of the amplitude with large momentum in the original EFT. Otherwise, it's not acting as a UV completion. and putting in that requirement fixes the coefficients of f squared in the action to come in the form of t mu nu. So the chi mu nu, the massive spin 2 state, has to scale like a massive graviton. So we'll show that in an upcoming paper. But here, okay, so I have 3 arbitrary coefficients, a1, a2, and b. Let me integrate out the massive spin 2 chi mu nu and generate the Wilson coefficients. And indeed, the Wilson coefficients care about all 3 couplings. They care about a1, a2, and b. But my d0, d3, d6, d9 only care about a1 and b. a2 ends up dropping out. And indeed, they generate d0 and d9, but they don't generate d6 or d3, and they come in a combination that's strictly positive. And when I plug this into the Dyonic black hole bound, I again get something that's manifestly positive. It looks like a perfect square. So even for massive spin 2, we get positivity. So just in summary, for these example completions, you don't generate anything that couples to the Wald tensor. You don't generate d3 or d6. You just generate the combination d0, which makes electric or magnetic black holes have z bigger than 1. And you generate d9, which gives you z bigger than 1 for the equally Dyonic QE equals QM black hole. So you live in this space here, and all of the rest of this space is forbidden by the requirement that delta S is positive. So a couple other consistency checks. Let me consider the case of only photon self-interactions. So I only have f to the 4th terms left, and I turn off the r squared and rf squared terms. We know what the bounds from the photon should be just from analyticity bounds. So running through the usual dispersion relation argument to bound photon-photon scattering in a way that Nimar Kanihamed and collaborators showed in an 06 paper. They showed that 2d7 plus d8 is positive and that d8 is positive. But we get exactly those same bounds coming out of our Dyonic bound when we turn off everything except d7 and d8. So that's consistent with the analyticity bounds. One final example is in the low energy description of the heterotic string. Let me just read off what the Wilson coefficients are. You can look them up in the literature, and they're the following. And let me plug them into our Dyonic bound or into our electric bound in general dimension. And we again get combinations that are manifestly positive. So the entropy of black holes indeed is larger than the Bekenstein-Hawking entropy in string theory. So just to wrap up and remind you what we've done, we relied on a universal notion of thermodynamic entropy, that delta S should be positive when there are more microstates added to a system for a given macrostate. And indeed, we proved this shift in entropy for the case of higher dimension operators generated by tree-level quantum field theoretic completions using a Euclidean path integral argument. And applying this logic to a system of charged black holes, we can compare the Wald and Bekenstein-Hawking entropies to bound the higher dimension operator coefficients of the r squared, rf squared, and f to the 4th terms, producing a family of bounds. And for the near-extremal black hole, these bounds imply the same positivity, the same combination of coefficients that also guarantees a positive correction to the extremality bound of black holes in the EFT. So consistency of black hole entropy ended up implying the weak gravity conjecture in the sense that the black holes themselves provided the requisite states. And as we saw, this generalized nicely to the case of multiple fields, arbitrary dimensions, and even to Dyonic black holes. But there's a lot of other things we can consider. It would be nice to apply this to a broader class of theories like Einstein-dilaton gravity. It would be nice, as you alluded to try and make this work for an ADS black hole, though we've been working on that, and there are some subtleties involved in making it work for ADS. One could alternatively do this for non-spherical metrics, and in every case you'll derive new classes of bounds on the higher dimension operator coefficients. More broadly, we'd like to understand the relationship between the entropy bounds and the bounds that come from analyticity, unitarity, and causality. They're sort of morally similar because the entropy bounds are fundamentally about state counting, right? Entropies are counting microstates. And bounds that come from dispersion relations, you write the Wilson coefficients as some integral over a cross-section. So you're also using state counting. The unitarity bounds are about state counting. So there's a fundamental similarity in what's at the core of the positivity in both of those arguments. It'd be nice to think about extended versions of the weak gravity conjecture. It would be really nice to ultimately get a bound on the particle content rather than the black holes alone. But the exciting thing is that there's a lot of work that remains to be done in separating the swampland from the landscape, and we continue to discover new tools to do that, like black hole entropy. So thanks very much. Yeah.
So do you these bounds were derived at tree level, right?
Yeah.
So first question would be, you might guess that somehow you should be able to derive the same bounds on the Wilson coefficients from some sort of consistency condition on tree level scattering. So
Right.
do you think that that's true, or what do you think about that?
Yeah, so this is something I've actually thought a lot about. There ought to be a way to bound these Wilson coefficients from scattering amplitudes, but the four derivative operators, these operators, the r squared, rf squared, and f to the fourth, are hard to bound using scattering amplitudes for the following reason. Just in pure Einstein-Maxwell theory alone, let's do photon-photon scattering. The two photons can exchange a graviton between them. And in the forward limit, that amplitude will look like s squared over t. G Newton s squared over t. Then plus something that looks like the di's times s squared. And you want to bound that second thing. But when I do my contour integral in the complex s-plane, I extract not just the di's, I also extract that crummy t-channel singularity that's always there, that you can't get rid of. So at fourth order in derivatives, that seems like a fundamental problem. At higher order in derivatives, you can just kill off the t-channel singularity by the residue theorem. So if I want to bound the Riemann to the fourth operators, I can do that because those will look like the Wilson coefficient times s to the 4. And indeed, I've done that using analyticity. So you can do it at higher order, but there's the t-channel singularity at this order. You can prove, though, using a spectrum representation argument that the Wilson coefficient of the Gauss-Bonnet term is positive, which I've done in a different paper. But that's not an amplitudes argument. Any other questions?
What about proving the entropy increase under the same conditions for black holes, but at loop level? Do you think there's hope of that?
There is a statement at tree level.
Pardon?
There is this statement at tree level.
Right. This is a statement at tree level. He's wondering if we could somehow prove that loop level. That would be nice, but the argument would have to look different than the Euclidean path integral argument I gave. Because if you have a loop level completion, say, just at cartoon level, phi squared r, where I integrate out some massive phi squared, you don't get to play this game of going off shell by setting phi to 0 because phi is 0 on the background anyway. So it would have to be a quite different argument, but we strongly suspect that it's true, just given that the implication is so simple. It's just that this inequality of free energies implies a weak gravity conjecture. That's true before you say anything about tree or loop level. So now it's just a matter of proving this inequality of free energies. Hard to say. We think it's true, but we're not sure what the best way to attack loop level is.
If there are no further questions, let's thank Grant again.
Thanks.